Welcome to Parametric Equations. Before we jump into parametric equations, I want to do a quick review of ellipses and hyperbolas and how you can tell the difference when you're looking at the equation. This is the standard equation for an ellipse, and you can see that both quadratic terms are positive. The standard equations for hyperbolas are over here, and you can see that either the x squared term or the y squared term has a minus in front of it. So one's plus and one's minus. And so let me just show you how to graph, the quick way to graph an ellipse or a hyperbola. So let's graph this ellipse. I know it's an ellipse because both quadratics are positive. Let's just plot the intercepts. If x equals 0, then y squared is equal to 4. So y is plus or minus 2. So that gives me intercepts 0 plus or minus 2. And then if y equals 0, then x squared is 25. So x is plus or minus 5. So that gives me intercepts plus or minus 5, 0. So this ellipse is going to be oriented along the x-axis. That's called the major axis, by the way, the axis with the larger intercepts. So this is 5, and then negative 5 over here, and then up here is 2. So this looks like an egg lying down. Okay, let's look at this equation over here. Again, I'm going to plot the intercepts. If x is 0, then y squared is negative 4. Well, that can't happen. That's impossible. Y squared has to be a non-negative number. So now I automatically know that x can't be 0, so I can't have that guy, and my parabola is going to open left-right, not up-down. So let's just find the x-intercept. If y is 0, then x squared is 25, so x is plus or minus 5. So this guy looks like this, opens left-right, and this is 5 here. All right, so that'll come up today. So parametric curves. I want to talk about how to sketch parametric curves by plotting points, using Desmos, or eliminating the parameter. A parametric curve is a curve with a parameter. Usually we use t as the parameter, and so you can see here, this is a parametric equation, and it's actually two equations in one. I've got x is t squared minus 4, and I've got y is t over 2. So sometimes people write that with parentheses as a single equation, and sometimes people write it like I have down here as two equations. Both are fine. We'll see in a minute that the Cartesian version of this curve is x equals 4y squared minus 4. Now that's a Cartesian equation. It only has x's and y's and no parameter. Whereas this is a parametric equation. It has a parameter. So the benefit of having a parameter is you can define a starting point. You can say, I don't want the whole curve. I just want t greater than or equal to 0. You can also define a direction and a speed. So it gives you more control. So the simplest way to sketch a parametric curve is to plot some points. And I've done that here. I've got a little table. I let t equal 0, 2, and 4. And I computed x and y. And then I plotted those points over here. So it looks like I'm getting the top half of a parabola, but I'm not sure. We'll verify that in a minute. Another way is to use Desmos. So let me show you that. With Desmos, the way it knows you want a parametric curve is you use parentheses and you use t as your parameter. You can't use theta or any other letter. So cosh t, comma, sinh t, those are hyperbolic functions. And then automatically it gives you a default on t. We want t going from negative pi to pi. So there you go. It looks like the right branch of a hyperbola. And actually it is. Okay. And then the really go-to way for sketching a parametric curve is to eliminate the parameter. And there are three methods here. I'm going to show you an example of each one. So let's just jump right in with that parametric curve from the first example. This again defines two equations, x equals t squared minus 4 and y equals t over 2. I can solve either equation for t. I'm going to pick the easier one. I'm going to pick the y equals t over 2 and solve for t. So that gives me t equals 2y. Now what I do is I plug that into the other equation. So now that top equation reads x equals t squared, which is 2y squared, because t is 2y, minus 4. So indeed, I'm getting x equals 4y squared minus 4. All right, that's a parabola. It's laying on its side. It's opening up, and when y is 0, x is negative 4. So this number here is negative 4. That's where the vertex is. Okay, so the instructions say, sketch the whole curve with a dotted line and the portion of the curve defined by the parametric equations with a solid line. So we've done the dotted line part, but the parametric equations are only for t greater than or equal to 0, so we're not going to get that whole parabola. In fact, let's just see where we're starting. If t is 0, then x comma y is, go to your parametric equations here and put t equals 0 in, and we see we're at negative 4 comma 0. So I know that this is my starting point, and I'm either going to go up or I'm going to go down. Let's see. To find out which way you're going to go, just pick any t greater than 0. So maybe t equal 2. And then compute x and y and see whether you're going along the top or along the bottom. So in this case, if t is 2, x comma y is 0, 1. So that's up here. So now I know I'm going this way. I'm getting the top half of the parabola. Okay, when you see trig equations, you want to use method 2. So method 2 says to use the Pythagorean trig identities. So what I've done is I've written out this parametric equation as 2 equations, and I'm going to solve for cosine t and for sine t. So cos t is x over 5, so I square that. Cosine squared t is x squared over 25. Sine t is y, so sine squared t is y squared. And now I'm going to use this Pythagorean identity. Cosine squared I can replace with x squared over 25. Sine squared I can replace with y squared, and that equals 1. So I see now that I have an ellipse. Okay, this parametric equation is defined for t between 0 and pi. So let's see where we're starting. If t equals 0, then x comma y, put t equals 0 into the parametric equations, and we get 5 comma 0. So we're starting here, 5, this is t equals 0. All right, we're ending at t equals pi. So if t equals pi, then x comma y is negative 5, 0. So I'm ending over here, and I know I have an ellipse, so I'm going to dot that in. I also know that the vertices are plus or minus 5, 0, and then if x is 0, y is plus or minus 1, so this is 1 up here. Now the question is, I'm starting here and I'm ending here. Am I going across the top or the bottom? So to figure that out, pick a number between 0 and pi, maybe t equal pi over 2, and compute x and y. So if t is pi over 2, x, y is 0, 1. So that means I'm up here, so I'm getting the top half of the ellipse. If there were no restrictions on t, I would get the whole ellipse. Okay, why don't you pause and practice? Try the next one yourself. Okay, I started us out here. I solved the x equation for secant and the y equation for tangent. And now secant squared t is x squared, and tangent squared t is y squared over 4. And I want to use the Pythagorean identity, 1 plus tangent squared t is secant squared. So I replace tangent squared with y squared over 4, and I replace secant squared with x squared. Now let's get that into standard form. Let's move the y squared over 4 to the other side. So I get x squared minus y squared over 4 is 1. So that's my Cartesian equation. Cartesian, again, just means x and y. And that's a hyperbola. And I know it opens left, right. Well, there's no restrictions on t, so I'm not just going to make these bold. It opens left, right, because I can set y equal to 0 and I get x equal plus or minus 1, so that's a 1 here. And so since there are no restrictions on t, I'm getting the whole hyperbola. Okay, so now an example of one using method 3, which is a little bit vague. We could use method 1 and solve one equation for t and plug it into the other equation. However, if we look at both of these equations, we see that they both have an e to the t in them. And so we could just solve one equation for e to the t and plug it into the other equation. For instance, we know x is 2e to the t. So e to the t is x over 2. Rather than solving all the way for t, let's just stop there and plug that into this equation here, y equals 3 plus x over 2. And there you go. It's a line of slope 1/2 passing through 3 on the y-axis. So it looks something like this. Okay, how much of that line are we getting? Well, we're starting at t equals 0. So when t is 0, x comma y is, plug 0 in for t, and we get 2 comma 4. So this is t equals 0 here, 2 comma 4. That's our starting point. And then to see whether we're going up to the right or down to the left, let's pick a value of t that's greater than 0. Let's say something easy to graph would be if t is, let's say, ln2, something with a log in it so that I can get integer coordinates for x and y. X comma y is 2 e to the ln2 comma 3 plus e to the ln2. Well, that's e to the ln2 is 2. 2 times 2 is 4. And then, this is a plus sign, 2 plus 3 is 5. So 4 comma 5, that's up here. So I'm going in this direction. All right, now there's certain curves that are very easy to parameterize, and here they are. Line segments, circles of radius a centered at the origin, and functions y equals f of x. And you can use this Bible to help you parameterize certain curves. So let's do an example of each one. Here we've got a line segment from -1, 2. So this will be my x0, y0 in the Bible. And then 3, -2 will be my x1, comma, y1. And I'm just going to use these equations here. So we get x of t is -1 plus 3 minus -1, which would be 4t. And then y of t is 2, that's y0, plus -2 minus 2 is -4t. So let me just clean that up. X is -1 plus 4t, and y is 2 minus 4t. And then it's important, if you only want the line segment from one point to the next point, you want to restrict t to go from 0 to 1. If you don't, you'll get the whole line. We just want the segment. So that's just plug and play. This one's even easier. We want a circle of radius 2, because x squared plus y squared equals 4 is a circle of radius 2. So we're going to let x equal 2 cos t and y equal 2 sine t. And since we want to go once around the circle, we're going to let t start at 0 and go to 2 pi, not including 2 pi, so each point gets counted once. And there it is. If we wanted to go twice around, we let t go from 0 to 4 pi. All right, and finally, line segment. I'll switch up the notation here. I'll use the single equation, x comma y equals, from our Bible, x is t and y is f of t. Well, f of x is x squared, so f of t is t squared. This one causes the most trouble with students because it's so easy, it's almost scary. And t is going to go from a to b. And in this case, a is 2 and b is 3. You want the x values. So 2 to 3. All right, and that's the end of this section.